For the physics colloquium today. Antia got her PhD from Santiago in Spain. And prior to joining to ASU, she was a postdoc at Argonne and UC Davis. Her research involves electronic structure calculations of correlated materials, such as unconventional superconductors and frustrated magnets, which today she is going to tell us about the new exciting research on nickel age of superconductivity.
Hear me okay? Yep, perfect. Yeah, so thanks, Honor, of course, for the introduction. And it's actually very exciting for me to be here after a while and see so many familiar faces without a screen in between, at least, and without a mask, I guess. So yeah, as Honor mentioned, today I want to tell you a little bit about this new age of superconductivity that we believe it's currently unlocking, that it's the nickel-based one. So what I'm going to tell you about today has been inspired by the discovery of the first nickel-age superconductor back in 2019. So that was, of course, a very important discovery in and of itself, but also because we believe it may give us the keys into some long-standing mysteries in the context of high-temperature superconductivity in the cuprates as well. So this here is a brief outline of the talk. Given that we are going to talk about superconductivity today, we better know what that's all about. So I'll just give you a brief general introduction, highlighting some of the concepts that we are going to use later on. I'll then tell you about some of the key ingredients that always seem to appear in the copper-based superconductors or cuprates. These are to date the materials that have the highest critical temperature, at least at ambient pressure that we know of. So that's why it's important to know what are they all about. I'll then move on and tell you about the class of materials that we have been studying for the past 5 years or so, which are what I like to call low valence layer nickelates. And I'll then finish by telling you a little bit about what I think it's left to do. So as I said, I wanted to start from the very beginning. I'm pretty sure that you all know that superconductivity was discovered back in 1911, actually by a student working with this gentleman down here, Heike Kamerlingh-Owens, who was a pioneer himself in working with materials at low temperatures. The big surprise came when they cooled down mercury wire, and they found that the electrical resistance actually drops to 0 at around 4 Kelvin. So this magical temperature at which the resistance vanished is what they ended up calling the critical temperature, or TC, of the superconductor. The second key property of superconductors came quite a bit later in 1933, and it's what we call the Meissner effect. So what Meissner and Oxenfeld found was that below that magical critical temperature, a superconductor expels a magnetic field. So it's not only a perfect conductor, but also a perfect diamagnet. Importantly, this field expulsion will repel a nearby magnet, and that gives rise to what is, to me, still today, one of the most fascinating demos that we do in class. That is that of a magnet levitating on top of a superconductor. The superconductor that you see down here, it's actually a cuprate. It's a material called a YBCO, and we are going to talk more about that later. And also we are going to understand why is it that you need to throw in liquid nitrogen in there as well. This effect, it's really cool, at least to me, but it doesn't go on forever. If you actually apply a large enough magnetic field, superconductivity can be destroyed. And that that field, sorry, it's the field that we call the critical field of the material. On the theory front, things were also moving. And fairly quickly, Fritz London realized that the properties of superconductors that I just told you about implied that electrons in them actually behave in a collective manner. And at the time, this was quite controversial in that bosons which have integer values of the spin, we know can behave in this fashion, but electrons, which are fermions with half integer values of the spin, do not. The apparent contradiction, though, was solved by Leon Cooper when he demonstrated that the presence of even a small attractive interaction between the electrons could actually cause them to form pairs. So these Cooper pairs behave as effective bosons indeed. And we know now, of course, that pairing is actually a necessary ingredient for superconductivity. Now we know that, but why would the electrons want to pair? Well, something must be gluing them together. And according to the most celeb theory for superconductivity, that is the Bardeen, Cooper, and Streifer, or BCS theory, the adhesive is actually phonons. And phonon-mediated electron pairing is the way in which we understand what we call conventional superconductors. So the way in which this works is the following. As you see in this cartoon, what you have is a mobile electron, that is this blue guy here, that attracts the slower moving ions of the crystal lattice, that are the red guys that you see with a plus. So you can see in this area how they squeeze together, and that ends up producing a knot of positive charge that then ends up attracting a second electron. And that ends up leading effectively to an attractive interaction between the electrons themselves. These conventional BCS superconductors are characterized by what we call S-wave pairing. And the reason why I highlight that here is because this is going to become important later. When I talk about the cuprates, we'll see that the situation is actually quite different. In the conventional guys, which are again superconductors that are characterized by S-wave pairing, what this means effectively is that electrons in conventional superconductors can pair in any direction and can sit on top of each other so that the wave is a sphere. Or if you like, as I mentioned here, you could also say that the spatial component of the Cooper pair superconducting wave function is isotropic. Again, once we get to the cuprates, you will see that the situation is quite different. So BCS theory, it's of course great, and I think that there is very good agreement that we understand what the mechanism for superconductivity is in the conventional superconductors. But ideally, you would also want to be able to predict new superconductors. And that's where things haven't really worked that well. But of course, throughout the years, different people have been trying to formulate different design principles to try and predict new superconducting materials. And perhaps the most famous set of rules are those that were set by Bernd Mathias, who was an experimentalist himself. And his rules were the following: high symmetry is best, peaks in the density of states of the material are good, stay away from oxygen, stay away from magnetism, stay away from insulators, and probably most importantly for him, stay away from theories. So hopefully, as a theorist myself, I'll show you today that we have some use into this, but he had his good reasons to think in this way, and I think he ended up discovering over 1,000 superconductors himself, actually. So the years went by, and more superconductors were being discovered. What you see in this graph is just a plot of TC versus here, and in kind of red, even though here it looks darker, you see different superconducting materials. But you can also see that the TC didn't really go up by much, somewhere around 20 Kelvin in the span of 60 years, right? So not very good, especially if you're looking for a room temperature superconductor. But a big surprise came in 1986 when these two gentlemen, Bednorz and Müller, discovered the first copper oxide or cuprate superconductor. That first cuprate superconductor was the one that you see down here at the bottom, this lanthanum barium copper oxygen system. You can see that its TC may not be or may not sound very high, 40 Kelvin, but again, in the context of the superconducting materials that we had up to that date, it was quite a big jump in a short period of time. Even more importantly, you can see that more and more cuprates were discovered very, very quickly with higher and higher critical temperatures. And among those, one discovery that was particularly important was that of this yttrium barium copper oxygen system, or YBCO, that is the one that I showed you before in the demo of the magnet levitating on top of a superconductor. The reason why the discovery of this guy was so important is because it was the first one whose TC was above the boiling point of liquid nitrogen. And mine liquid helium or liquid hydrogen, sorry, is probably not a very cheap thing to do, but liquid nitrogen is not so expensive, probably the price of beer or milk, whatever you like best. So the technological implications of these were, of course, very profound. Now, cuprates are just different. And all of the rules that I told you that Bernd Mathias had postulated and that were very successful for him in finding new superconducting materials basically break down here. First of all, cuprates are complex materials in terms of their structure. You can see here the crystal structures for quite a few different cuprates. So you can see that in all cases, and this is probably better, we have copper, oxygen planes. So the copper is here in blue, the oxygens are in red. So in all cases, again, we have these copper oxygen 2 planes. This is just a zoomed in version of one of those, where the copper has basically a square planar environment of oxygens. And again, this is common to all of the cuprates that you see here. This is effectively where the action is in the material, as we're going to see later on. In between those planes, we have spacer ions that can be, as you can see here, mercury, barium, yttrium, lanthanum, strontium, and a few others. And effectively, the way in which superconductivity comes about is by doping carriers into those spacer planes, and you always dope into a parent material that it's an insulating magnetic oxide. So again, stay away from oxygen, stay away from magnetism, stay away from insulators, really doesn't work here. But of course, that comes at a cost. And the cost is that more than 3 decades after their discovery, we still do not fully agree in terms of what is at the origin of high TC. There are very good ideas, but I would say there is not a quantitative theory yet. So there are people that say that it's waves of magnetism that are responsible for pairing, playing a similar role to the one that phonons play in the conventional superconductors. Others say that it's patterns of charge or current or even phonons that actually play the key role, and it may even be a combination of all of those. So there are plenty, as you see here, of theories connected to high TC in the cuprates with a lot of controversy and a lot of very strong opinions, I would say. But rather than getting today into what we don't know, let me just highlight a few things that we do know for sure. And one thing that we do know, because there are experiments on this, it's about the shape of the quantum wave that describes the paired electrons in the cuprates. And it's shaped, as you see here, like a 4-leaf clover. And this we call the wave shape, means that the pair electrons sit on adjacent copper ions, but never on the same ion. So this is already quite different with respect to what I told you before that happens in the conventional superconductors. So we say here that the pairing state is unconventional instead, as it features an order parameter that is now anisotropic. Remember that in the conventional ones, we had an isotropic one. One other thing that we know about the cuprates is that we always have strong antiferromagnetic correlations. That's measured by something that we call exchange interaction, and you will see me using this letter J throughout the talk. I may also call it super exchange. And this is for the cuprates then very large, somewhere around 120 MeV. And the reason why it's large is because in the cuprates, we have a strong degree of hybridization between the copper D and the oxygen P orbitals. And you can see why that's the case in this cartoon, where we have the lobes of the copper D orbitals in red directed towards the P orbitals of the neighboring oxygens that are in green. So as such, this has been perceived as an attractive source for pairing. And even before these experiments, there were already theories that were based on this fact and that had already predicted D-wave pairing as well. In cuprates, there is also good agreement in terms of certain properties that are common to all the materials and that change with the amount of doping. And those are reflected in a prototypical cuprate phase diagram, which is what you see down here. where in the y-axis we have temperature, in the x-axis we have hole doping, or a change in the chemical makeup of the material. A very similar phase diagram, by the way, can be obtained for electron doping, but the one that we can map to the nickel H is this one. That's why I'm going to focus on that today. So in the cuprates, we always start at the corner of the phase diagram, for which the parent material has coppers that are in a 2+ configuration or valence state, which means that it's a D9 ion to begin with, if you like. So for that fill-in, what we have always is an antiferromagnetic insulator. Then you start doping the material. At some point, superconductivity appears, keep on doping further, reach a maximum in TC in this dome, somewhere around 20% doping. That's this D8.8 fill-in. You keep on doping even further, and at some point, superconductivity just goes away, and we enter what is called the overdope regime, where we should be finding a metal. That's, of course, a simplified view. There are plenty of other phases in this phase diagram, but for today's purposes, that should be enough. So before I move on, let me then recap and summarize what are these key ingredients of the cuprates that I'm then going to try to contrast to the nickelates. So remember that in cuprates, first of all, we always have a layer structure to begin with. We have our quasi two-dimensional lattice based on our copper oxygen 2 planes. In addition to that, in the parent phases, the copper is always in a 2+ D9 configuration. That leaves us with a spin 1/2 system with strong antiferromagnetic correlations and the involvement of a single band of dx² minus y² character around the Fermi level. And I didn't tell you how this one comes about, but it's kind of easy to see if you try to feel the D levels for a D9 ion in a square planar environment, which is what we have in the cuprates, so that you end up having just a single hole in this uppermost dx² minus y² orbit. Last but not least, in cuprates, remember, we also have a strong degree of oxygen P and copper D hybridization, which once again, you can see in the cartoon I showed you before, where we have the lobes of the dx² minus y² orbital of the copper directed towards the p orbitals of the oxygens. So this is all great, and we know a lot about the cuprates. Then how do we solve the puzzle? And what has been perceived as a plausible strategy to try and shed some light into what are really the ingredients that are key for superconductivity is to try and find cuprate analog materials, meaning materials that may be very close to cuprates in a certain way, but that may also have some differences, and that ultimately can help you pinpoint what are really the ingredients that I need here for superconductivity in the end. And if you go back to the periodic table and you locate copper into it, you may start to think that there are a few things that you could try and do. You could go right and go to zinc, but zinc 2+ is non-magnetic. That's probably not a very good starting point. You could go down and go to silver, but in oxide, silver actually wants to be a valence keeper due to the difference in crystal field. It likes to be 1+ or 3+, but not 2+. So again, probably not a good starting point. Or you could go left and go to nickel. And of course, you know that I want to tell you about the nickel H of superconductivity today, so that's the route we're going to take. But before I do that, I just wanted to mention that concerning the silver route, there has been some progress in the past 2 or 3 years, actually looking at silver fluorides instead, rather than oxides. So what people have been looking into is this material here, silver difluoride. In this case, silver is actually happy being in a 2+ oxidation state. And what has been found in this is that in this system, one can actually get a large super exchange as well, somewhere around 70% of what you get in the cuprates. However, this material has no spacer layers, so it cannot be doped, at least in the way in which cuprates are doped. And the structure is more 3-dimensional like. Remember that in cuprates, we have all of this quasi 2-dimensionality that may be important. But again, food for thought, and maybe we'll have a surprise on that in a few years. But again, you know that I want to tell you about the nickel H of superconductivity today, so let me come back to the nickelates. We already know, of course, that nickel and copper are by one another. In the periodic table, In addition to that, nickel 1+ is actually isoelectronic with copper 2+. So the ideal here would be, well, if I'm able to stabilize materials in which I can have nickel in this oxidation state and in which the structure it's maybe close to the cuprates, maybe I have a fair shot. And the family of materials that realizes this paradigm is the family of materials that I like to call low valence layer nickelates. This is a family of materials that all contain infinite nickel oxygen 2 planes in analogy to the copper oxygen 2 planes of the cuprates. So you see those guys all the way here. This is probably the bigger one, so easier to see. In blue, we have the nickel here, in red, the oxygens. So you see how we have exactly the same type of planes that I showed you before for the cuprates. This up here is the general formula for this family of materials, where R, it's a rare earth ion that can be lanthanum, praseodymium, or neodymium. And this N factor that you see appearing in a couple of places tells you how many of those nickel oxygen 2 planes you have along the Z-axis. So for N equals 2, you have the bilayer material. For N equals 3, the trilayer material, and so on, all the way up to the infinite layer member of the series. Unfortunately, these materials cannot be synthesized directly in this very nice layered form, but one actually has to get here from parent phases that do have apical oxygens. The reason for that is because nickel is not very happy being in a 1+ oxidation state, even though that's what we want. You have to get here again from parent phases in which nickel is a little happier. And then our experimental colleagues are able to do all of this alchemy to be able to remove those apical oxygens out and end up with these nice layered cuprate-like phases, which is what we want. So let me show you how that works, at least for one material of the series. That is the infinite layer member. That's this R nickel oxygen 2 material, or 112 material. So here again, we have our nice layered phase with our nickel oxygen 2 planes that are separated by a single layer of the rare earth ions. But again, the way in which we get to this material, it's from a parent phase, that is this perovskite phase, or 113 phase, in which we do have apical oxygens. So what they do is they put the material in a hydrogen environment in very tricky conditions, or so I'm told. And that's basically how you end up with your nice layered phase. If we do simple ionic count in this material, R is a 3+ ion, oxygen is 2-. What you end up getting, it's a nickel 1+, that it's a D9 ion, or a pseudo copper 2+, which is what we want. And the surprise came in 2019 when it was found that by a doping, one can actually get superconductivity in these materials. This is work by Harold Huang's group in Stanford. This was, as I mentioned in the beginning, the first report of superconductivity in a nickel oxide material ever. And more specifically, the system in which they found superconductivity is whole doped neodymium nickel oxygen 2 that has a maximum TC that it's around 15 Kelvin. You may say, okay, it's not very high, but again, we'll see later that that may help us understand certain things that could perhaps help in pushing that up. So effectively, the way in which superconductivity comes about in this material, it's very cuprate-like, if you want. If we come back, sorry, to the cuprate phase diagram, we start with a material here at the corner, a D9 filling, hold dope it, bring it into the dome, and that's where superconductivity arises here as well. What you see here on the left, by the way, it's what they call the Yenga chemistry, because basically that's how they pull out the apical oxygens. So of course, today, I would like to tell you a little bit about what is our perspective from the point of view of electronic structure theory for this infinite layer nickelate. But I would also like to tell you about other layered nickelates of the family. More specifically, the tri-layer material, which we actually looked into before superconductivity was discovered in the infinite layer guy, and also the 5-layer material, which we have found recently. It's the second superconducting member of the series. This is, of course, as I put there, with the ideal in mind, that we may be here in front of a whole new family of nickelate superconductors rather than just a single isolated random superconducting material. As I go, what I would like to do is to contrast the properties of these nickelates with some of the cuprate key ingredients that I told you about in the beginning. More specifically, the proximity to D9 filling with the presence or absence, we will see, of a single bond of the x squared minus y squared character, the presence or not of strong antiferromagnetic correlations, as well as of a strong PD hybridization. Now, before I move on, let me repeat the same type of ionic count that I did for the infinite layer material for the other two compounds so that we can see where they sit in the cuprate phase diagram. Remember, for the infinite layer material, what we have, it's a nickel 1+ ion, that it's a pseudo copper 2+. If you repeat the same exercise for the tri-layer compound, that is this 438 material, what you end up having, it's a nickel 1.33+, that's 867 d electrons per nickel on average. For the 5-layer compound, that is this 6,512 material, what you have instead is a nickel 1.2+, that it's a D8.8 ion. That may not tell you anything, so let me come back to the cuprate phase diagram to kind of see where all of these systems sit. The 112 material, as you saw before, falls at the corner. You then hold dope it, bring it into the dome area of filling. That's where superconductivity has been found. The tri-layer material instead falls into the overdoped regime, where in principle, if a naive one-to-one analogy to the cuprates were to work, you would expect to be finding a metal. The 6,512 materials instead fall directly at optimal doping, where if again, this naive one-to-one analogy were to work, you would expect to find a superconductor. And I already broke the news and said that that's what we found. But before I go into that material, let me tell you about the famous guy. That is the infinite layer or 112 compound, in which we have been working in collaboration with Andy Millis and Mike Norman. And much of the work that I'll show you today that we've done has been actually done by a very brilliant PhD student, Harry Labolita, and also by a very talented, now former postdoc, Jyoti Krishna. So one thing that I didn't tell you about the infinite layer compounds is that even though superconductivity has just been found, these materials have actually been around for a long time. The first report goes all the way back to 1983, so even before the discovery of the cuprates. However, I believe the problem might have come from the fact that when they were looked into in the cuprate context, people quickly realized that they were not very cuprate-like. Remember that for cuprates at D9 filling, you expect to find an antiferromagnetic insulator. It turned out that in these materials, there is no signature for long-range magnetic order, even though we now have evidence of strong antiferromagnetic correlations. And as I'll show you in a second, the resistivity actually shows metallic behavior. So again, not quite like a cuprate. And I guess that's probably what made people think for quite a few years, well, this is not very promising. Let me move on to something else. And by people, I probably mean ourselves too. But of course, we know that we were totally wrong because superconductivity in these materials is actually possible. So this here is just a snapshot of the original Nature paper from Harold Huan's group, in which they looked at films of neodymium nickel oxygen 2, that's the parent phase, and also of 20% whole doped neodymium nickel oxygen 2. So what you see down here is the resistivity versus temperature curve. For the parent phase in red, you can see it's metallic at high temperature with a low temperature upturn in the resistivity. For the doped system in blue, also metallic, but with a big surprise that it shows a superconducting transition whose onset is more or less at around 15 Kelvin. What you see on the right is just one bit of the magnetic response. This is just the temperature dependence of the magnetoresistance, where you see that we have very little magnetoresistance in the normal state, and then a suppression of superconductivity upon an increase in field. There are some other parameters here that I'm going to talk about later on when I get to the 5-layer system. So that was the original paper, but throughout these past 3 years, people have worked quite hard on this. And we now know that also the lanthanum and praseodymium analogs of these infinite layer materials are superconducting as well. And we also have a wide range of doping dependencies that show that we have a cuprate-like dome in these materials as well for the dependence of TC. So what did we decide to do? Well, we first wanted to look at the basic electronic structure of this material using density functional theory. And we looked at first, of course, at the paramagnetic electronic structure. And what we wanted to do was actually to contrast this nickelate with its cuprate analog, that it's calcium, copper, oxygen 2. And these two materials are actually isostructural. So what you see on the left, let me see if this works better. It's just a prototypical cuprate band structure in which we have just a single dx square minus y square band crossing the Fermi level. That is just our horizontal line there. In the nickelate case, you see that the situation is kind of similar. You keep on having that band, but you instantly see that there is something also quite different in that you have these extra bands crossing that I marked here in red. And those are neodymium 5D bands. So in the nickelate, one starts already a D9 filling from a non-cuprate-like situation in that you already have self-doping of that large dx square minus y square Fermi surface due to these neodymium D bands. And at the time, we thought that these neodymium D bands were indeed the ones that were at the origin of the experimentally found metallic behavior, which is something that upon there is an agreement now. The electronic structure that I just told you about, it's also consistent with the whole data, and you will see me contrast theory and experiments because we always think that that's an important bit to do. What you see here is the temperature dependence of the Hall coefficient. For the undoped material in red, you can see it's negative at all temperatures, and then for the doped material in blue, that it actually has a sign change. So this is kind of already evincing that you need this type of two-band picture that I just told you about. This would otherwise be inconsistent or very hard to reconcile with us having simply a large hole-like Fermi surface like you have in the cuprates. Now, these materials, of course, have strongly correlated electrons. So we wanted to look at correlations a little bit more carefully using dynamical DFT plus DMFT, that's density functional theory plus dynamical mean field theory, that it's a more appropriate tool to actually look into that. And in particular, we wanted to look at what is the role that those neodymium D states play. Are they simply an spectator, or do they actually play a deeper role into the electronic structure of the material? So what we find in DFT plus DMFT is that the basics of the electronic structure that I just showed you remain. You can see that here in the spectral function, other than, of course, for renormalization effects. The correlations, importantly, are dominated by the dx square minus y square orbital. That's a pretty cuprate-like scenario. What we find is that the neodymium D states are weakly correlated. They simply act as a charge reservoir, but they don't have a much more active role into the electronic structure of the material. And this was quite important at the time because people were trying to decide whether those neodymium D states actually had a deeper role or not. As I'll show you in a few slides, this picture is actually consistent with what you find in the other superconducting member, that is the 5-layer material. Moving on to the degree of PD hybridization, a way to measure this is actually to look at a quantity that it's called charge transfer energy. So this measures the splitting between the transition metal D and the oxygen P states. So remember that in the cuprates, we have a large degree of PD hybridization, and that translates into a small charge transfer energy. Here you see that charge transfer energy plotted for quite a few different cuprates that are the different blue points. So you can see that the maximum value that you can get for this charge transfer energy in a cuprate, it's somewhere around 2.6 eV. Again, that's reflective of the high degree of PD hybridization. In this nickelate instead, what we end up getting, it's a value of the charge transfer energy that is somewhere around 4.4. So double the value of what you get in the cuprates. And you can instantly see why over here, this is just the nickel D density of states for a couple of orbitals, the dc square and dx square minus y square. This is the oxygen P. You can see that these states are very far apart. If you were to look at a cuprate, they are much closer together. So the charge transfer energy is larger. That translates into a super exchange that it's still sizable, somewhere around 60 MeV. But remember that in cuprates, you were around 120, so much smaller, which may also account for the lower TC that you have in this material. Now, just to tell you a few words about doping, remember that when we dope is when superconductivity arises, so it's important to look at how does the electronic structure look like there. What we find is that it becomes more cuprate-like. How does that translate into this? Well, what we have is that the rare earth D pockets become depopulated. You can see how they shift to higher and higher energies as you dope. So they move farther away from the Fermi energy. There is this vertical line here again. In addition to that, the charge transfer energy decreases with doping. What you see here is how the oxygen P states also move to higher energies, while the nickel D states that are somewhere around here are actually not moving. I didn't plot them here, but you can take my word on that. So the charge transfer energy again decreases, and that it's once again consistent with experiments. These are X-ray absorption experiments at the oxygen KH for the dope material, where you can see that we have a pre-peak that I mark here by the arrow appearing. This doesn't exist in the parent compound, and that's generally an indication of the presence of oxygen holes. So again, consistent with that, and also with what is found in the cuprates. So all in all, these infinite layer nickelates seem to have quite a few similarities with the cuprates, but also important differences, in particular, this larger charge transfer energy or lower PD hybridization, if you prefer, and the involvement of rare earth D states. But what we wanted to understand, rather than focusing too much on the infinite layer compound, which we actually did, was to understand how do all of these differences and similarities fit in the context of other layer nickelates of the family, because what we were thinking about was trying to establish a whole family of superconductors, again, rather than just a single superconducting material. So that takes me then into the second part of the story that I wanted to tell you about today, and that's the story of the 5-layer nickelates or 6,5,12 compounds that we have been looking at in collaboration with Julia Monti. So remember that the 6,5,12 or 5-layer nickelate falls directly at optimal doping, where again, if this naive one-to-one analogy to the cuprates were to work, you would expect to find a superconductor. And as I mentioned in the beginning, that's indeed what we have recently found. So this here is a snapshot of the experiments done by Julia's group on films of neodymium 6,5,12, which is again the 5-layer nickelate. You see at first the resistivity versus temperature, where we have once again a superconducting transition whose onset is once again at around 15 Kelvin. Not much better, but there may be room for improvement with improvements in the materials, which are ongoing. What you see on the right is the same bit of the magnetic response, where we have a suppression of superconductivity upon a magnetic field that is applied perpendicular to the plane of the sample all the way up to 9 Tesla. One can get from here the coherence length and of course also the critical fields. They are very similar to those of the infinite layer compound as well. But what about the electronic structure, which is what we do or what we look into? So for this material, what we have is 5 nickel dx square minus y square bonds that are the red guys crossing the Fermi level. We have 5 bonds because this is the 5-layer material, so you have 5 nickels. We keep on having a certain degree of involvement of rare earthy states that are these bluish or turquoise guys. But these pockets are much smaller, so there is a reduced role of the neodymium D states in the material with respect to the infinite layer counterpart. This is once again consistent with the Hall data that is now positive at all temperatures. So basically this tells us, or at least that's our perspective, that perhaps nickel D and neodymium D hybridization is that indeed not a required ingredient for superconductivity in these systems. Moving on to the degree of PD hybridization or charge transfer energy, we get here a smaller value. Remember, for the infinite layer compound, it was 4.4. Now you go down to 4 eV. Once again, this is consistent with the appearance of a pre-peak at the oxygen KH in the X-ray absorption. Now, what about pairing? We haven't talked about that at all. We actually paired on that with Honor Ayrton. And for the infinite layer material, already people using quite a few different methods had determined that very likely the dominant pairing instability was in the dx squared minus y squared channel, like in the cuprates. And what we found is that the same situation stands for the 5-layer material as well. So all in all, this 5-layer nickelate seems to be kind of similar to the infinite layer compound, but a bit more cuprate-like if you want, in that you have this larger PD hybridization and a reduced role of the rare earthy states as well. But what we thought was very shocking, of course, was that this naive, if you like, cuprate-motivated prediction of optimal doping at D8.8 had now given us superconductivity in 2 different nickels by, again, using that simple analogy, right? Both in the 112 or infinite layer compound, through which, well, you get here through chemical doping in that material, or you can also do a layering of the dimensionality, and that's how you get to this point for the 5-layer or 6,5,12 compound instead. So that takes me then into what could be next. How can you tweak another material to actually do that? And what we think could be next, it's actually materials that we have been looking at for quite a long time, probably since 2017 or so. And those are the tri-layer members of the series. And this is, again, part of a multi-year campaign. That's how John Mitchell actually likes to call this. And again, it's work that has been done in collaboration with quite a few different people over the years, Warren Pickett, Mike Norman, John Mitchell, John Freeland, and Martin. So if you remember, but that was way too many slides ago, the tri-layer or 438 nickelates fall into the overdoped regime of the cuprates in terms of electron count, where if we extend our one-to-one analogy, you expect to find a metal. Now, is that what you find? Well, yes and no. You can see here the resistivity versus temperature curves for the lanthanum material that you can see is highly insulating with a transition at around 105 Kelvin towards more of a semi-conducting-like regime, but definitely not a metal. The praseodymium counterpart instead, praseodymium 438, it's metallic all the way through, no signature of any transition whatsoever. So the lanthanum material actually wants to charge order, and that's the reason why it behaves in this way. Then through a chemical pressure effect, the praseodymium material doesn't charge order, and it's pretty happy just being in a metallic state. So I'm not going to focus on the lanthanum material today, even though that's very interesting in and of itself. Let me just, though, tell you a few words about the praseodymium counterpart, that it's, if you want, the more cuprate-like of the two. So remember, for this material, what we have is an average nickel valence of 1.33 plus. That's, again, 8.67 d electrons. What we found, once again, using density functional theory, is that in this material, the nickels are happy being in a low spin state, and you can completely forget about what that means. Effectively, what that translates into, it's on the fact that you have, once again, just a single dx squared minus y squared band per nickel crossing the Fermi level. You have here 3 nickels, so just 3 bonds. While now the rare earthy states are actually higher in energy. They are these guys here. They don't cross the Fermi level anymore. In addition to that, in this system, the charge transfer energy, it's even smaller. We went from 4.4 eV in the infinite layer to 4 eV in the 5-layer to now 3.6 in the tri-layer. So as you lower n, or the number of nickel oxygen 2 layers, you lower the charge transfer energy, or you increase the PD hybridization if you prefer. That also results in an increase in the super exchange. And it's once again consistent with the presence of a pre-peak at the oxygen KH in the X-ray absorption once again. So at the time we thought, okay, and you can say this is 2017, it's great that you get a metal where cuprates are metals, but nobody wants to be finding a metal, you want to be finding a superconductor. So already what we thought at the time is, well, if this material falls in the overdope regime of the cuprates, what if I now electron dope it with a 4+ ion like cerium? And that had been done in quite a few cuprates in the past. And I'm able again to explore that side of the phase diagram. But again, you can see that that's 2017. So something must have gone off. And what went off is that it turned out that experimentally it was very hard to dope these materials. But I think that the discovery now of superconductivity, not only in the infinite layer compound, but also in the 5-layer compound, could perhaps bring renewed energies to try the doping of these systems a little harder. And who knows, they may just be the next superconducting members of the series, or at least that's the hope. Even if that were not to work, it's not all lost. One could also try the 6-layer or the 4-layer members of the series that you see here in dashed, because they have never been synthesized, but they will give you direct access to the dome area of filling once again without having to dope. So again, hopefully our experimental colleagues who have been so brave all the way through will have progress on that soon as well. But for today, I have no more news on that. So I'll just stop here. I hope, though, that I've been able to convince you that this family of low valence layer nickelates, it's really exciting. I think that they are emerging as their own class of superconductors with similarities to the cuprates that we have seen, like their square planar nature, the dominant role of the x square minus y square states, or the presence of a superconducting dome centered at around 20% hole doping, but also with some important differences, particularly the larger charge transfer energy or lower PD hybridization if you prefer, and the involvement of rare earth d states at the Fermi level. So I think, though, that now that we have 2 members, we can say pretty confidently that we have here a family of superconductors. And as I say there, hopefully we will have more members joining soon. And hopefully we will find the YBCO nickelate equivalent with a much higher TC. But again, for today, that's just, something in the brain, not being realized. So I'll just stop here. I'll just leave you a snapshot of the work that we've done on this in the past few years. And I will, of course, thank you a lot for your attention.
Thank you, Antia, for the great talk. Any questions?